We know that when we plug 2 into this, it needs to spit out what? 41, right? So let's do that. We're going to put but v of 2 equals 41, which implies that when we plug in 2 into this velocity function, we should get 41. 2 here, we should get 41 at the end, right? And now we just do some arithmetic here. What is this here? 48, take away 12. What's that? 36. So 36 plus c is 41. So c must be what? 5. So now we've nailed down exactly the velocity function, haven't we? We know exactly what it is. So I can come and edit my answer. Come back. You know what? I'll do it somewhere else. I won't do it right there. So now what we have is, we know our acceleration. Our velocity function is exactly the function 12t squared minus 6t plus 5. All right, Michelle, you already did your long division, so I'm not going to call on you. I'm trying to get through these names. Octavio? Yes? All right, so you following? What's the next thing? We need to get to acceleration, right?
Well,
I'm sorry, I said acceleration. Position. Yes, thank you. We need to get the position function, right? So how are we going to get the position from the velocity?
we get the next antiderivative.
Yeah, take the next antiderivative. So how do you feel about the antiderivative of this? I'm just not quite sure where everyone is in the class. I know some students, I can already tell they've done this and they can probably tell me that antiderivative without writing anything on a piece of paper. But I'm not sure where everyone else is, you know, so.
This is the second antiderivative?
This is the second time we've done it, because we've gone from acceleration to velocity, right? Now we're going from velocity to position. All right, so should we take it slow? Bring the 12?
Yeah, bring 12.
Okay.
Multiply it by 1 over
1 over
2 plus 1.
2 plus 1, so I'm going to put 3. And then t to the
And
3, okay. And then what about that? Minus 6t. So bring the minus 6.
Yes.
Okay.
It's 1 over 2.
1 over 2. T
2.
t to the 2. And then plus, let's see, antiderivative of a constant is
5t.
5t. And then plus, I'm actually going to call it d this time. Okay, only because C we did in the earlier part, and I just don't want us to have two different C's. We could go back and call the first one C1 and call this one C2, but here I'm just going to call it C and D, all right? It's still just some number I don't know.
So we're replacing the C with a D now?
Yeah, just because I don't want to have C in two different places that wind up having two different values. All right, so cleaning this up, we get 4t cubed minus 3t squared plus 5t plus d. Tavio's done. Martin? Where's Martin? Well, Martin, I think you know what to do, yes?
We'll plug in 1 and 7.
You plug in,
The 1 and 7?
yeah, so we know 1 goes into this, it should spit out 7,
Yeah.
right? So we say, but S of 1 equals 7, which implies that when 1 goes into this, 1 cubed minus 3 times 1 squared plus 5 times 1 plus d, that we need to get out 7, right? And then you just solve this for capital D. Okay. This should clean up. What is all this? 6. Okay, so we get 6. Oh, wait, 6. Yeah, 6 plus d equals 7. So d is 1. So now we have d, which means we've nailed down the position function, haven't we? And that means we've answered part A. So the position function is 4t cubed minus 3t squared plus 5t plus 1, because we found that d is 1. So does everyone agree we found the position function of the object? Exact position function. So how do you answer part B? You just plug 2 into that. That's it. Okay? Plug 2 into that. I don't think I'm going to do that. What does it turn out to be?
31.
31, so this would be 31. Now, I don't know about you, but when I was in Cal 2, I actually found this to be somewhat remarkable, what we just did. In this sense, what did we know? What was the only thing we were given here? The acceleration of an object, right? If you know the acceleration of an object, you can actually recover exactly where that object was at every point in time. But you just need a little bit more information than the acceleration, but not much more, right? The only thing you need is a little information about its velocity at one point in time and its position at one point in time. If you can give me just that, I can give you exactly where this thing was at every point in time. I can tell you its speed at every point in time. And of course, I can tell you the acceleration at every point in time because I was given that, right? Does that not seem remarkable that you can gather that much information about an object by just having that little piece of information? Let me show you this in another way. Maybe another way that you might appreciate it more. When we're on Earth and we drop an object, what is the only force acting on it? Gravity, okay? So what is the acceleration of gravity? So gravity has an acceleration function on Earth of what? Negative 9.8 meters per second or something like that? Okay, somebody, well, I'll do it right here. (9.8 meters to feet). About 32 feet and some change, okay? About 32 feet, all right? So the acceleration of gravity on Earth, right, is negative 32 feet per second, all right? So if I drop an object on Earth, that's the acceleration of it, right? That's it. Now we're taking air out, okay? You have to take air out of this. You want to throw air in there, it becomes more complicated, right? But for now, let's just go with that, all right? Now, what is the velocity function for this object? Yeah, this is the antiderivative of this. So what is the antiderivative of 32? Okay, negative 32t plus some constant. Do you all agree? So I've got a family of functions now, don't I? Nobody has given me any information about this object, have they? So I don't have these two pieces, do I? But here's what I do know. Here's what I do know, is that I can say v of 0. When I plug 0 into this, what would v of 0 be? What would my velocity be at 0 time? It would be c, wouldn't it? If I replace that t with 0, this is c. So instead of writing c here, here's what I'm going to write. V of t equals negative 32t plus v subscript 0. And that number right there is really c. But that's the velocity at the beginning. That's your initial velocity, right? Because time is 0. Does that make sense? Yeah. Okay. Now, let's find the position. So what's the position function? Sorry, I'm trying to hang up my phone. Second antiderivative. So what's the antiderivative of negative 32t? So you go through your little thing and you have a 1/2 t squared in there and all that. And what do you get? Negative 16 t squared plus, what's the antiderivative of v0? v0t, right? Because that's a constant. Plus some constant we don't know, right? Call it d. But I do know something about this. The position at 0 should be what? At 0 time, it should be d, right? So let's not call it d. Let's call it something else. Let's call it s of t equals negative 16 t squared plus v naught t plus, let's call it, I don't know, s naught, our starting position. And do you recognize this formula? Right? This is your falling bodies on Earth, falling objects on Earth. Okay? So you're taught either in physics or hopefully in an algebra class, you're shown this formula when you're getting applications of quadratic functions, that if you drop an object on Earth, this right here will tell you where it is at every point in time, so long as you know how high it started, its starting height, and you know if it had any initial velocity, like whether or not it was thrown up or thrown down or just let go. That formula, where does it come from? That's it. That's all we needed, right? So take me to a different planet, give me a different acceleration, and I'll tell you how fast things are going to drop there. Does that make sense? It's independent of anything except the acceleration on the object. So for the moon, there is a quadratic function that tells you where things are going to be when you drop it. And all we need to do is be able to measure the acceleration of gravity on the moon to come up with the formula. So anyway, I hope that helps you illustrate a little bit better why I still find this pretty mind-boggling that you can go so far with something so little in the beginning. All right, let's see what else we have here. Oh, that's it, homework. All right, we got 20 minutes, so we've got just enough time to kind of dip our feet in here to the next section. All right, so when it comes to antiderivatives, we kind of have, we don't have categories, we just have kind of like frames of mind. The first thing that you always want to think about when you're doing an antiderivative is this something, is it something okay? Like, e to the x. You should know what the antiderivative of that is. You should know 1 over x, what the antiderivative of that is. Cosine of x, you should know what the antiderivative, these are things that you should know, right? Is it x to the n? Because you know there's a formula for that, right? So there's this whole category of things where we should be able to handle them. And then after that, we start to completely lose any ability to have a formula. You know how in Cal 1 there's formulas like product rule, quotient rule, chain rule, all this. We don't have that here. It's too complicated to go backwards. So what we have are techniques. We have approaches, things we try. And the first one that we're going to try is substitution. That's your first technique. After we learn substitution, we're going to learn something called integration by parts. You'll come to love that. And then we'll have, after that, we'll have trig integration. Now, when you see the word integration right now, integration means antiderivative. Just think of it that way for now. Trig integrals, then we'll have this monster, something called trigonometric substitution. After that, we'll have partial fractions, or partial fraction decomposition. I'm just going to say partial fractions. So this is kind of in a nutshell, the next few weeks, is we are going to be trying to find antiderivatives, and we are going to be trying to use these sorts of approaches to do them. All right? Something you should know, substitution is, after this, substitution is by far the easiest on this list. Integration by parts is problematic. Trig integrals, Trig sub just causes people major headaches, and partial fractions, that hardens you right there. Yeah. And at any point in time, we'll see what's happening is to do number 2, you better be good at 1. Because you'll use this to turn it into something like that. And then to do this, you need to be good at both of those. And then to do that, you must be good at all those. So everything builds. You can't say, oh, I'll figure that out later. You're kind of dead in the water if you get stuck on any of these methods. Yeah. All right, so the next section is substitution. Okay, so this is the substitution rule. But before we do it, there's some notation. So I need a way of telling you that I want you to find the antiderivative. Okay, this me writing little f and then saying go find capital F, we just need a better notation for it. So I'm going to introduce you to some notation, and for now I just want you to accept it. All right, so from now on, if I ever want you to find the antiderivative of some function, what I'm going to do is I'm going to write this right here. I'm going to write this symbol, which is called the integral sign, right? It's all written down here. Then I'm going to put the function in here like this, whatever the function is. And then at the end, I'm going to tack this thing called dx onto the edge of it, all right? So all of these things have different names, right? Integral sign, this is called the integrand. This is called the differential. Anything else I'm missing? Oh, the capital F of x over here is called the antiderivative. And the c actually has a name. It's called the constant of integration. All right, so all of this is just notation. And for those of you who've done Riemann sums, I will explain why we use this symbol and what all these things mean later. For now, this is a short way of me telling you to find the antiderivative. All right? All right. So as an example, what's the answer to that? X squared plus c. Right? So this is the first problem we started the day with. I said, hey, everyone, go find the antiderivative of that, right? And we said, oh, that's x squared plus c. All right? So this is telling you go find the antiderivative. This differential part is vitally important, but right now just look at it as just part of this symbol. Okay? Like it's just, these are kind of together, they're telling you to find the antiderivative. All right? Can you just accept that for now? Okay. Here's a way that I don't want to walk away from this. I want to really kind of explain what that is a little bit more. I'm going to ask you to take derivative of this right now, okay? What is derivative of this? And let's go real slow. 2 would come out, right? 2 times x to what power? 1. Now the chain rule would say times, now I'm supposed to do derivative of the base, right? And what's the derivative of x? It's 1, right? So I could put like dx there, right? Like the derivative of x, but this is really kind of like a 1 for us, isn't it? So do you see that if I take the derivative of this, I actually do get 2x dx? Do you kind of see that? It's just that's really kind of a 1, but we need it. We need it. We need that here for what we're going to do, all right? All right. The process of finding antiderivatives of functions is called integration. All right. So in Cal 1, we do differentiation. That's finding derivatives. In Cal 2, we find antiderivatives, which is called integration. So normally in a calculus sequence, Cal 1 is called differential calculus, and Cal 2 is called integral calculus. Integral meaning integration. Yes? Don't do that? I did it. I did it. Do you want me to redo it? It's on camera. All right, so we've already seen the power rule. We know all the common ones that we should be familiar with from Cal 1. And now we get to substitution. All right, so with substitution, I'm going to do this by working backwards, okay? So what I want us all to do here is take the derivative of that. Okay, so everyone let's take derivative of this. Sine of x squared. So what is the derivative of that? So first derivative of sine, right? So cosine of x squared, right? Chain rule times derivative, what's in there? 2x, right? Yes? All right. So if I rewrote this, I could write that 2x cosine of x squared, right? Same thing. Now that you know this, could you find the antiderivative of x cosine squared x? I'm sorry, I said that wrong. Can you find the antiderivative of x cosine of x squared? Well, isn't that almost x cosine of x squared? The only difference is I have a 2 here, right? So what would I have to take the derivative of, right? What do I take derivative of to get that? That's what this is saying. What do I take the derivative of to get this? What is it? Y'all aren't following this. Yeah, it's sine x squared, right? But almost, not quite, right? Because if I say that it's sine x squared plus c, then the derivative of that is that, so I'm off by 2.
Would be just
So yeah, just put a 1/2 in front, right? If I put a 1/2 in front of that, so if I take derivative of that, I get what I'm looking for, but I have a 2 there. I don't want the 2, so I put a 1/2 out here, so it kills it off. Now this is not substitution. I'm just trying to show you that going backwards is not easy, right? Finding the antiderivative of this, the only way we really knew what to do is because I started with the problem up here, right? So imagine you didn't know this. You started with that. How do we get to this, right? So that's where the substitution rule comes in. So here's the way I look at substitution. Substitution is taught many different ways. Kind of different approaches. This is the way I see it. This is the way I present it to my students. So for substitution, or you might hear me call this U sub, or you might hear some other math people talking about, call it U sub. What we do is this. We take a look at the integrand. Okay, so you look at the function you're trying to figure out the antiderivative of. You look at it, you stare at it, and then what you want to look for is you want to try and find something within the integrand, and you want to see its derivative somewhere in the integrand. So let's take a look at the problem that we were just doing. Okay, that was a problem that we know the answer to this, right? It's 1/2 sine x squared. But if we started with this, you would sit back and say, okay, I'm going to try substitution. Well, you would first say, this is nothing I know, right? This is nothing from Cal 1 that I know the antiderivative of. So you'd sit here and go, all right, well, do I see something and its derivative? So I'm going to help you see it. Do you see that x squared? What is its derivative?
2x.
2x. Do you see 2x? You see x? That's almost 2x, right? Almost. So I'm saying here, look for something in its derivative. The derivative should appear in the numerator. So the something I saw is here, right? It's trapped inside cosine, but its derivative, x, is right here in the numerator. There's no fraction, really, but it's not trapped. It's just sitting there, right? You'll see it? And the derivative might be off by a constant. Is our derivative off by a constant? Yeah, it's the derivative of that is 2x, right? We actually have x, not 2x. So I've identified something in the problem. I see its derivative. It's not trapped. It's off by a constant. I'm good to go, right? Like according to the first 4 things here. So the next step is for us to make a substitution. We're going to let u be that something. That's something that we saw. What was the something we saw? X squared, right? So here we go. This is the actual technique. I'm going to now say, let u be x squared. I think I'm going to start this on a clean sheet. All right. I'm going to let u be equal to x squared. Now, next step. I'm going to differentiate that equation with respect to x. the derivative of the left side with respect to x is du dx. The derivative of the right side is what? 2x. All right? I've identified something. I looked for its derivative. It was there. It wasn't trapped. It was off by a constant. So I let that something be u, and now I'm differentiating it with respect to x. The next thing I'm going to do is I'm going to isolate du. I'm going to put du, multiply both sides by dx, and I get 2x dx. So this is 2 times x times dx multiplied here, right? Now I'm going to play a game. And I'm going to go back over to my integrand over here. And I'm going to see, do I have this somewhere? Well, do you see the x? Do you see the dx? You don't see a 2, do you? But you see that? So what I'm going to do is I'm going to get this by itself on one side of this equation. So how can I get this by itself of this equation? I want this here. Leave this here. So just divide both sides by 2. So this becomes 1/2 du equals x dx. If you're confused, just let me do a few of these, and hopefully it'll start to become clear to you. All right. So you see what's in blue here? Right? You see the blue? You see that blue here, right? All right. You see the red here? You see that right there? I'm going to rewrite the whole integral now. I'm going to rewrite the problem, and I'm going to basically dump my x's and make everything u's now. So when I rewrite this, what does the x dx become? Half du, right? Half du times, what does cosine of x squared become? Cosine of u. With me? All right, you see that 1/2? I'm going to pull the 1/2 out. Why am I allowed to do that? Why am I allowed to pull the 1/2 out in front and not worry about it? Because it's a constant, right? And we already talked about when you have constants in front, they're just going to kind of come along for the ride. Okay, and now all I'm left with in here is these two pieces, right? So I'm going to rewrite them backwards. And now that right there is asking you to find the antiderivative of what? Cosine of u, right? Do you know the antiderivative of cosine of u? Just sine u. Just sine u, right? So this becomes 1/2. Now I'm actually finding the antiderivative now, right? So I'm not going to write this symbol anymore. I know the antiderivative of that is sine of u. And then sine u what? Plus a constant, right? Sine of u plus a constant. Am I done? No, because my answer has u's in it. What was my original problem? Has x's. So now replace u with x squared. And isn't that what we said it should be? Isn't that what we said the answer should be? That's it. Yes?
So the du is just turned into c? Or whatever?
It didn't. The du doesn't turn into c. Remember I said that when you see this, just kind of ignore these and say, what's the antiderivative of this? But if you want to think that that turns into c, do it, because it might help you like not forget the c. But technically, that's not what's happening. Okay, I have 2 minutes. Let me do one more. I just want to see if you can see something and its derivative, okay? So how about this one? What am I doing? Yeah. Secant, that's not secant. Secant squared of natural log x over x dx. There we go. I have like 30 seconds. Ricardo, just say yay or nay. You're here or not. Jeremiah?
Here.
Christopher?
Here.
Mohammed?
Yes.
Gina? Jacob? Stephen, y'all are looking at that right now, trying to find something in its derivative. Erica? Jace? Edward? Arafat? I've got you. Christian? Gabriel? David? Luis? Luis? Got it right finally. Heidi? Chris? Jonathan? Tatum? And Rasul. Okay, everyone's here. All right, does anybody see something and its derivative? What's the something you see? The natural log of x. What is its derivative? 1 over x. So if you kind of need to do this, you could rewrite this. That's the same thing, isn't it? I mean, that's the same expression. The x on the bottom is really like a 1 over x on the side. So if we make a substitution, u is equal to natural log x, the derivative of that with respect to x should be 1 over x, right? And now if I isolate du by multiplying both sides of this by dx, now I can try and play this little matching game. I'm trying to see if somehow this appears over here somewhere. And it's exactly here, isn't it? I mean, that is it. Perfect. So I can replace the 1 over x dx with what? Du. And I can replace the natural log of x with u. So this will now become secant squared of u du. Y'all see how everything just got replaced? And now what's the antiderivative of secant squared? Tangent of u, right? Tangent of u plus a constant. But what's u? Natural log of x. So this should be tangent of natural log of x plus c. And if you don't believe that that's the antiderivative, take the derivative of it. The derivative of tangent of something is secant squared of it times the derivative of what's inside, which is 1 over x, which would give you this part, and you're there.
Shouldn't that be over x?
No. Mm-mm. We are going to do more of this, obviously. You can do your homework for 4-7. Okay, do that, and then we're just starting 5.5. Question? Let me turn off my camera.
You said it shouldn't be trapped. Isn't it trapped inside of that secant?
Okay,